Okay, so now that we've used the first derivative to determine our relative extrema and intervals where the function is increasing or decreasing, we can move on to discuss the concavity of the function. And the concavity, we use the second derivative to determine. So for part D, they want us to find the intervals where f is concave up or concave down. And so in order to do that, first we need to figure out what our second derivative is going to be, because we know that in order for the function to change concavity, our second derivative would have to change sign. And that happens where our second derivative is either 0 or does not exist, kind of like our critical numbers with the first derivative, or where our function could change from increasing to decreasing or decreasing to increasing. So we've already determined that the derivative of f, the first derivative of f, is 4x cubed minus 12x squared. So its derivative, the second derivative, will be 12x squared minus 24x. And we want to know, where is this equal to 0? Or possibly where is this undefined or does not exist? To find where it's equal to 0, again, this one's pretty easy to solve by factoring. Both factors have a common factor of, or 12, both terms have a common factor of 12. And both terms have a common factor of x. So if I factor a 12x from my 12x squared, I'm left with just x. If I factor 12x out of the 24x, then I'm left with 2. And so we have that either 12x could be equal to 0, or x minus 2 could be equal to 0. If 12x is equal to 0, then x equals 0. If x minus 2 equals 0, then x equals 2. And again, since our second derivative is a polynomial, it's a quadratic, we know it's defined for any value of x, so there aren't going to be any values of x that would cause the second derivative to not exist. So we've got two possible places where our second derivative could change sign, meaning that we could have a change in concavity. So again, I'm going to draw my number line. I'm going to put in where the second derivative is equal to 0 at 0 and 2. And I'm going to look at the sign of the second derivative to determine what's happening with my function. So let's start with a value that's less than 0. If I plug in a negative number, then 12 times the negative number is going to be negative. So my first factor would be negative. If I plug in something less than 0 and subtract 2, then I'm also going to have a negative. So I have a negative product times, or a negative factor times a negative factor is going to give me a positive product. If I plug in a value that's between 0 and 2, say like 1, then 12 times that value is going to be positive. 12 times a positive number would be positive. But if I put in something less than 2, like 1, then when I subtract 2, I'm going to get a negative value. So now I have a positive factor times a negative factor. It's going to give me a negative product. And finally, if I plug in a value in this region, some number that's greater than 2, it's going to be positive. So 12 times a positive gives me a positive here. And if I plug in a value that's bigger than 2, like say 3, and subtract 2, it's also going to be positive. So now I have a positive value times a positive value is going to give me a positive product. And so previously we said that if the second derivative is positive, we know that the graph is concave up. If the second derivative is negative, we know that the graph is concave down. So this region must also be concave up. So we can say that f is concave up where x is less than 0 and where x is greater than 2. And we know that because the second derivative of f is positive or greater than 0. We can say that f is concave down in between 0 and 2. And we know that because this is where the second derivative is negative or less than 0. Again, make sure you write out your intervals and write out your justification for full credit. The number line alone is not enough justification. You have to state it explicitly. And finally, part E wants us to determine the values of x where we have inflection points. Now that we've looked at our intervals where we're concave up and concave down, we can very quickly see the inflection points as being the places where we change concavity. So we change from being concave up to concave down at 0. We change from being concave down to concave up at 2. So we have inflection points at x equals 0 and at x equals 2. And again, because our original function was a polynomial, we know that those are going to be actual points on our graph because our function will be defined for any value of x. So we don't have to go back and check and make sure that those are points on our function. So we could just simply say that f has inflection points. At x equals 0 and 2. Because the second derivative changes from positive to negative, or vice versa.